more coming or what's going on?
Yes, sir.
They are coming? Okay, then let us just wait for 5 minutes. So we need now, if you are going here to the 301 folder, here we go, and then we need going back. So there it's also figures layer inclusion, yeah, this one. No, that's the wrong one, I think. Then you are going back again. Go to your stick. So and then you are going no. Yeah, you are going here to inclusion. Maybe it's this one. You are continuing these pictures we had already. Yeah. Moment. And you are going down. This one is now the first one for today. Are they writing away again a test or what? Some. So yeah, let us start. We start. I showed you just in the week before we went to the field trip these pictures from Greenland, and there we saw how such a layered intrusion looks like. So now the question is, how can we produce magmatic layering? Yeah, I mean magmatic layering occurs only in silica undersaturated rocks, yeah? So that means we have in the norm no quartz. Yeah, these are the olivine-bearing rocks and nepheline-bearing rocks, silica undersaturated rocks. So and therefore we have now to think about why it does only occur in silica undersaturated rocks and not in saturated rocks. So therefore we have now to check the viscosity. So because silica saturated rock has a higher viscosity compared to a silica undersaturated rock. So and that is, if you are checking how silica is coordinated, then you should know by now from the ES301 that silica is tetraedric. Yeah? You know this by now, but I can make just again a sketch map if I can have the board. Okay. So you know that certain elements you will find in the tetrahedrons, and other elements you are finding in the octahedrons. Yeah, you should know this now from ES301. So and now we have to think about that we have not done in ES301, but now we are doing this. Why is a silica saturated belt then has a higher viscosity compared to a silica undersaturated belt? Yeah? There is a total simple reason. So I mean such elements like silica, titanium, aluminium could be, but must not be. Aluminium could be tetraedric, but or it can be octaedric. So because it's the aluminium bubble is a little bit smaller compared to the magnesium bubble, which is always octaedric, but it is a little bit bigger than the silica. So, and you know by now how such a tetrahedron looks like. So that looks like this, yeah. This, yeah, then we have the tetrahedron, and the silica is sitting inside in the tetrahedron. Yeah, you know this by now, that is the silica for a plus. So, but it could also be the titanium, or you can replace it by aluminium or some other elements. Yeah, so these are tetraedric coordinated elements. So, and then you know by now as well from the ES301, here on the corners, you have the oxygen, yeah? So, and now we can, the oxygen, yeah, the oxygen bubble has O2 minus, then one negative charged electron is sitting here, and with the next one you are connecting that to the next tetrahedron. Yeah, then you have here the next tetrahedron. Yeah. So like this, and then we have here the next silica. So, and then we have in here the next oxygen bubbles. So this oxygen bond is now satisfied, one electron is sitting here and the other one is here, and therefore you can connect it. So and then we can connect it here to this side maybe. So and then you have here the next silica, and here you have the next oxygen bubbles. One is sitting here behind, yeah. The next one is sitting here, the next one is sitting here. So, and then we are connecting here the next one. So, and then it is like this. And then we have this. So, and then you can connect it here. Here you're connecting then here like this, maybe, yeah. Then you have here the next connection like this. So and so on, yeah. I mean, I must now not continue because then it is endless, yeah. So, but you can just make it for yourself and you will see it fits always together, yeah? So, and that is why a silica saturated belt cannot have layering, yeah? And therefore the silica saturated belt has a higher viscosity because all the tetrahedrons getting then making a network, yeah? So, and therefore a silica saturated belt does is not that mobile like a silica undersaturated belt, yeah? So because in the silica undersaturated belt you are making not this network, and then all the different different elements forms then the different minerals, yeah, like olivine and pyroxene and all this stuff, yeah? Plagioclase, of course, is always with us. So and therefore this undersaturated belt, they show with a lower viscosity, therefore they are faster. So in there you have then a lot of single crystals. I mean here we have a crystal-free magma, yeah? So and then this magma cools then down. So and then we have here the liquidus. Here we are forming the first single crystals, yeah? But you do not have any network, yeah? They are just swimming around, and you know those one with a lower density, they are floating up to the top, and the other one, which has a higher density, they are sinking then down, yeah? So and here, you have just a suspension zone. Here we have a convective boundary, and between the convective boundary and the rigid boundary, we are starting to produce a crystal mush. So because more and more single crystals getting connected with each other, yeah? So after the rigid boundary, you are forming then a rigid crust containing 50 to 100% of crystals. So and if you have then formed more crystals, then your belt becomes stuck. Yeah, because then it's rigid, and then you have no longer a flow, yeah? So in such a silica saturated belt becomes stuck much faster because of these connections, yeah? So and that is caused by these elements which are tetrahedrally coordinated, and the most common one that is most common element, tetrahedrally coordinated element, that is the silica atom. So and then you have network modifying elements. So and these are the the metals, you know, magnesium, iron, calcium, all these guys, yeah. So and they are making not these connections we see, yeah. And the silica undersaturated belt is much more enriched in magnesium, for example, or iron or calcium. compared to a silica saturated belt. Yeah? So that's the reason. So if you are producing then this stacking process, then you are creating this magmatic layering. Yeah? So you can produce, or if you are would like to observe this in your daily, on your daily base, then you can watch how a magmatic layering works also in the traffic. Yeah, if you are just going back. Yeah, here you have all these magmatic layers. Yeah, can you see it? Yeah. That is like the remnants of a cow, yeah? Looks exactly like this. So there you have these magmatic layers, and therefore you are always enriching different different magmatic layers. They are always produced when your different minerals getting then stacked, yeah? And afterwards you are forming the next layer, and afterwards the next, yeah? So if you are would like to observe this in daily life, then you must just go out here at 5 o'clock on the Lantana Main Road, yeah? And then you can produce it, yeah? So because if the flow from the cars, from all the cars, becomes higher and higher and higher, the traffic, yeah? So then you don't need a traffic light or something like this, or a crash. If there are more and more cars on the way, even if the whole street is free, at a certain point it becomes stuck. Yeah, you can observe this. Yeah, I mean a single car or two cars can go through like hell. Yeah, if you have thousands, then the whole stuff becomes stuck. So again, it's here the same. You are forming then more and more minerals out of your crystallizing melt, and then it becomes stacked. And afterwards you are doing this again, and then you are producing the next layer. Yeah. So I mean here this connection then is a chemical process, which ends up then in a physical process. So at the formation, that you are getting here more and more layers, because here you are dealing with silica undersaturated rocks. You have then just so many crystals that it becomes stacked, like the traffic here in the Alcala Main Road at 5 o'clock in the afternoon. Did you get this? So, and I mean, I have uploaded, or Satan has uploaded also the description of all this, yeah? That you can just go through it and read it, yeah? So now we can continue with the figures here. So again we have then here finally the solidus, and here we have the solidified rock, which consists of 100% of crystals. So next slide. So now what's going on in such a magma chamber? You know that is a very important process. It's not only for the ES303, it's also for the ES301. And it is a very, very important process if we are talking about ore deposits. Yeah? So I mean, it does not matter if we are talking now about the chromium ore deposit, or if we are talking about the gold ore deposit, or if we are talking just about our hot springs in Vanuatu. So I mean, in such a magma chamber, different things are going on. You have at first a crystal-free magma or melt, yeah? Maybe 1200 degree hot, 1300, can even have more. You know, the first olivines with a formaldehyde content or ratio of 90, they are formed temperature of 1890 degrees Celsius, and you know this from your melt bananas, which I have given you in ES301. There I have given it to you for the first time. So and then you got them also in ES303 already again. So and therefore I must not give them now again in ES301. So you have your crystal-free magma, and that cools down, yeah. I mean, at first it includes somewhere, could be a chamber, but I don't think so that there is a hole where melt included. Yeah, there is also a thing. And what people still working nowadays, because in old petrology or geology, they are thinking always there's a hole, and there the melt is just included, placed inside. I don't think that could be, but I think that it's just pure nonsense, because I think the Earth's crust would look like that, like a Swiss cheese. You know, there is a hole, there is a hole, there is a hole. So I think it works something like this. Like you are putting two pieces of metal together by welding. Have you observed in your life a welder? Yeah? You are putting two pieces on top of each other, or next to next one, something like this, and then you can weld it. So and then you are starting to weld at one point. Here we have a piece of metal that you are connecting here with another piece of metal or tin. Yeah, if we are using it for a car, then we are using not real metal, because it makes the car then always slower as it is already. You are just using tin, with a thickness of maybe 1 millimeter or 0.8, something like this. So, and then the welder starts at one point, maybe he starts here, and then you can observe how it's welding through, yeah? So there is then a red bubble which goes through, yeah? Have you seen this sometimes in your life? Otherwise we should visit in this class a welder. Is there a welder here around besides our guy from yesterday?
Engineering.
What?
Engineering.
Yes, can you arrange it for next week?
Okay.
They should just put two pieces of metal together, and then they should weld it, or I can weld it by myself because I know how to weld it, yeah?
Okay.
Yes. So again, that is important to understand. Then this heating point goes through and through and through. So if I'm heating then somewhere too long, yeah, then your bubble becomes here bigger and bigger, yeah. So and that means you are connecting then, or you are mixing the material from here, from your welding point, with always with new material from outside. So and that is the thing what I have also told you last week a lot of times. That is then in the ES303, but most of you are sitting in the ES303. That is then the assimilation and the contamination from the surrounding material. So again, it's the thing what I think how a magma chamber works. But I have at first to publish it, because otherwise nobody will believe me, and you have to believe me. So then what we have here, we are crystallizing here a mineral. And this mineral is then in this case sinking to the ground, yeah? Because it has a higher density compared to the surrounding melt. So and that is then according or regarding or because of the Stokes law, yeah? Stokes law you know from ES301. So and therefore these minerals are sinking down, and that is actually the classical way, yeah? That is actually the classical way. The heavier minerals sinking to the ground, the minerals like plagioclase, a calcium-rich plagioclase in a mafic melt, has then a lower density that is swimming to the top, yeah? So that is our classical thing. And for those of yours, nobody of yours have been with me in Coro, yeah? Because last year I was sick. Otherwise I would have brought you to Coro, sorry for that. So and there you can observe it, because you are just with somebody from Coro. Both. So but there you can observe it. I mean, you have a lot of undersides in Coro, yeah? You can just walk around. I mean, Coro Island is not that big. You can walk around in 3 days. Yeah, we walked around through the whole island in 3 days. It is just 17 kilometer in north-south direction long. Yeah. So and then you can walk over a whole magma chamber. So because there you can then see undersides, plagioclase bearing undersides. These are then undersides which were formed not at first, but the melt, the plagioclase bearing melt, erupted at first because plagioclase has a lighter density, as I told you right now, yeah, compared to the surrounding melt, yeah. So, and I mean, we have here some andesites. These are andesites from Fiji, yeah. Yeah, but these are not good andesites, because these are pyroxene-bearing andesites. You need an andesite which contains plagioclase. Here we have plagioclase-bearing andesite. So it is all class. This one. Just checking for this andesite. So and then you have some other. Yes, that's great. Then we have a heavier mineral sinking to the ground. And there in Coro, the heavier minerals, these are olivines, yeah? They have a high density compared to the surrounding melt. Then the other mineral, that's the clinopyroxene and the lead, yeah? So then you can walk over a sequence on Coro Island where you are just stepping over andesites which contain, then in this case, these are Fiji andesites, and in this case, they are containing here big minerals of, I think, pyroxene, yeah? So, and if you have an andesite, which contain the big white crystals inside, then you have the andesite, then you have a plagioclase-bearing andesite, yeah? So again, it's the just differentiation caused by density. Yeah? So, but there are also some other things to think about. That is that we have here at the rim or at the boundary to the surrounding rock, we have a chilled margin. Yeah? And the chilled margin, that is a very fine-grained rock, yeah, because of what? What is the reason if you have, or if you are producing a very fine-grained rock? Yes, that is rapid cooling, yeah. So that cools down very fast because it comes in contact with the much colder surrounding country rocks. So if you are going then there, there you are, it cools then a little bit slower, yeah. Then you have here a more coarse-grained rock. Here it becomes really coarse-grained, and here you are forming then the residual melt, yeah. So if you are looking at this model, what do you think? I mean, if it cools down and very slowly, then you have here in this residual melt, which elements are enriched there? Are this residual melt shown as more parts rich or less parts rich? Less parts, yes. But if you have the more parts, then it's the residual melt. More parts, and you have then also more potassium group elements, because these are incompatible elements, and they are becoming then enriched there, yeah? But other elements like mafic elements, or like if you are looking for the bushveld in South Africa, there you have a huge chromium ore deposit. Chromium, you have noticed by now, chromium becomes removed very, very early in the magmatic process, yeah? Because chromium you will find in silica undersaturated rocks, yeah? So chromium forms then, for example, in the bushveld, whole about 1.5 meter thick layers, where you can just dig it with a digger, yeah? So therefore the element chromium, that is the thing which you can find in layer diffusions. I think you got this now. Yeah, the next slide. So here we have two models from the solidification front, yeah? So the solidification front, that is this front next to the surrounding rocks, yeah? So that is this rock, this front here. Where is the ruler?
Lower campus.
That's a lower campus. So then we have, I mean, here we have the solidification front. So when that cools then down at the outermost part, it cools down very fast. So and then it cools down more slow and slow and slow. So and that is now here for a single saturated aqueous and metal alloy solution. Yeah, that is important. That was just a single emplacement of a melt. Yeah. So a single emplacement of the melt. And it was saturated. I mean, you have a lot of aqueous in solution there, and the metals, yeah, and the metals. So, and I mean, the metals in this case would be platinum group elements, yeah. So, and if you have this single emplacement, then you are forming then such a strongly layered solidification front. So here we have another model, so and that is dominated by a lot of small crystals. Yes, they are just lying here around. Here you have some bigger ones. Here you have at first smaller ones, then you have here also bigger ones. How can you create this? And that is a typical example. If you have multiple emplacement processes from different magma pulses, yeah? So because then you have maybe at first you have a magma impulse creating then here these bigger crystals, and the second one shoots them through and creates then the smaller ones, or you are doing it vice versa, yeah? So that is then the scene, how it looks like at the solidification front. And if you are going back to our cow picture, this one, yeah, that's the cow picture. So then you can here see all the single solidification fronts, yeah. So and therefore these layer intrusions are very important for this for metal ore deposits. Yeah, it depends always because they are ultramafic or mafic in composition. Otherwise, you cannot create a magmatic layering. So and therefore, you will then form different ore deposits. Yeah. So, but that is just on the countryside. If you are looking for the ocean floor, I think these are actually such a thing I like often plant basalts, but the same high valuable elements like platinum, chromium, vanadium, and all these things, you will also find at the ocean floor. Yeah? Then we can go continue. Yep. So, and how does this then work? So here we have 4 pictures of minerals in a melt, yeah? So you have then here at sketch map A, you have then certain minerals and they are crystallizing, yeah? So, but they are not connected in the mafic or silica undersaturated melt over these oxygen bridges, yeah? They are just, I told you, you have the formation of all these single crystals, and then the certain, and if you are forming more and more crystals, while you are cooling down the whole rubbish, yeah, then the whole thing becomes then stuck and it becomes rigid, yeah. So and therefore you have here at first single crystals, and here you have the more single crystals with melt pockets inside, yeah. Here it becomes then really rigid, yeah, less mobile, and here it becomes then stuck. So and then you are forming between all these crystals these typical triple junctions, yeah. So in these triple junctions, here you have a wonderful one here, yeah. So and that is then just that shows you that this melt cools down then fast or slowly. Yes. Fast or slowly? Slowly, yeah? Because if you are cooling down something very fast, like this guy here, I saw it just today. Then you have here a melt that is actually less. That's an obsidian. That cools it down very fast, and there you will not find any single crystals inside. So, and then we are forming here these typical triple junctions, and these single crystals, while they have cooled down, they were then in equilibrium or not. They were in equilibrium. Because all these crystals cool down with the same cooling rate, yeah? So whereas if you have a melt and you are throwing it just somewhere in the bus, yeah? You know, in the bus room, yeah? So then it becomes shrieked, yeah, and then you have not this formation, yeah, but here you have wonderful triple junction. So and here you have still, if you have observed such a thing, or such a thing in thin section, yeah, that helps you then, this melt has become in contact with water, yeah, and then it just shrinks, and then you have still these melt pockets inside, yeah. So, and where do you think, where are the incompatible elements in such a situation or in such a situation? The incompatible elements, where they are. Are they in the melt pocket or are they in the crystal? Or they just left home? The incompatible elements, they are sitting here in the melt pockets, yeah? Because they don't like, they are not taken up by crystals which are formed early, yeah? They are not fitting inside the lattice, yeah? The crystal lattice, yeah? Because there is no space for them, and that is because they are too big, yeah? So next slide. So and that's the way how it looks like then in thin section, yeah? Here you have a lot of different leduclase crystals with the triple junction, yeah? So that, and here is a microcline maybe, no, it's not a microcline, I cannot identify. So here you have a fine-grained matrix and some bigger crystals inside, yeah? So and here it's also a little bit distorted, yeah? So and that tells you that, I mean, you are making thin section. Unfortunately, I cannot offer here a microscope class, yeah, because we have not enough microscopes, and we have also not, what else do we not have? About pores, yeah. Normally you should have 4 courses only in microscopy, yeah, and not geography and environment and all this stuff. But anyway, that's the way how it looks like in the black and white copy, yeah. Next slide. So here we have again such a representation, and we have a schematic representation of the crystallization of an ideal monomineralic rock. So what means this now? Yeah, that is just one mineral, yeah? So therefore you are forming at first, you have some minerals in suspension, yeah? And while you are cooling it down, then you are forming more and more of this mineral, yeah? So again, it depends when you are measuring these minerals. For example, let us say that these are olives, yeah? Or let us say these are leduclases, yeah? Let us go to leduclases. So if you know that the 2 end members of the leduclase, that is on the other hand, it is the amortite, yeah? That is the calcium-rich one. And then you have the albite, that is the sodium-rich one, and you know the number, the chemical formulas. Otherwise, if you had forgotten it, we have here the amortite, I make just AN, and here we have the albite, I make just AB. So, and then I make here the formula, then you have here calcium, Al2Si2O8. So in the albite we have here sodium and Al3Si3O8. This is 2 minus 16 plus 12. Then we have here only 1 aluminium, sorry for this, plus 3 plus 1. Yep. So, and here we are putting just 1 aluminium inside, because the calcium is 2 plus instead of 1, then we have plus 2, plus 2, plus 6, plus 8. So because we are removing 1 silica and putting here an aluminium instead of one silica here. That's the way how it works. And then we have here minus 16 fits. Yeah. So, and then they are cooling down, and you can see they have cooled down slowly because here you have all this triple junction inside. Yeah. So, and then you have, are you expecting the zonation of your pledging places? Yes. These pleasure places are then showing zonation, and if we are taking now this one, yeah, just this one, and drawing this one here, something like this, yeah, must not be exactly the same. So that is now this single crystal, yeah, this one. So and then you know that calcium-rich plagioclase is formed at higher temperatures compared to the albite, which is formed at lower temperatures. You know this by now, yeah? So again, this zonation looks like this. Maybe like this, and then you have here a hammer-type component, maybe of, yeah, just the number 90, yeah? So again, you are forming the next zone. Then you have here maybe an hammer-type component of 80. Then you are forming here the next zone. Then you have here maybe an hammer-type component of 70. Then you are forming here the next zone. Then you have an hammer-type component maybe of 60. And here you have hammer-type component of 50. Yeah, because it cools down, and then your plagioclase becomes from the rib to the core, or more enriched in sodium and less or depleted in calcium. Yeah, that is a temperature effect. Yeah. So, and what do you think? Or you have now sampled such a rock, and then you observe a zonation, but this zonation in your plagioclase, which you have studied or investigated, there you have another zonation. It is calcium rich at the rim and becomes then more sodium rich in the center. What happens then? Then this plagioclase grow while you have heated it up the whole thing, yeah? So and what is then the typical scenario behind that? Yes, because there you have just an injection from another magma or an influx from another hot magma in a more cooler magma. Yeah, and then you are growing plagioclases, but the zonation goes the other way around. Yeah. So and these are different situations. So and now you are cooling this down, and then you have here still pockets, yeah. You have here still pockets of melt, yeah. So, and if you have this situation, then we are talking also about annealing, yeah. Annealing means you have tempered your rock for a while at the same temperature, yeah. So then they can really crystallize and perfectly and become very perfectly in shape, yeah? So but that is then also something which tells you something about the mobility of the melt, yeah? I mean, this melt is very mobile, yeah? There's no doubt about it. So and then it becomes less and less mobile. So and if you would like to get some information how mobile it was, So, or if there is some fluid flow, yeah, between the grain boundaries, then you can just, yeah, come in, don't be shy, yeah. Then you can just check the minerals under the thin section. So, and therefore, we are going now to a paper of mine, yeah, because for the ES301 we have still a lot of time, yeah. Only the other one becomes short. So that is now something about grain boundaries from my own study. Because I'm studying also grain boundaries and the fluid flow. Yeah, it is still on your stick. I think I saw it there before. That is summer at all 2012. Yep. So that is a study which I had done when I was in Houston. So, and that was about the Colorado Plateau. So, and there I studied metal nodules, yeah, from the sump. So, and the sump is called sump because it is a volcanic neck. And you saw in the excursion, you saw a lot of different volcanic necks, yeah. So, and the Americans, they told them that's the sump, yeah. What is always so funny. There's nothing funny here. So, but anyway, I studied here the rocks from the sump. So, in this there are such metal nodules. I mean, that is a metal nodule from the Cornwall Island, yeah. I showed you it before, yeah, but it looks from the sump exactly the same. There are some olivines inside, or most is olivine. Here you have another one, yeah, that is from the Germany, this one, yeah. You have seen it a lot of times in class. So, and these guys I have studied when I was there. Well, let us say I have actually only taken the rock samples there because I was there in 2005 and I have studied them the data. I have studied that later. So in the Colorado Plateau, that forms actually something like an island. Yeah, you can see it from by using just Google Earth. Yeah, then just you can see it by using Google Earth, or you can just draw it by hand. Yeah. I have drawn it here by hand because in another paper I have such an overview left from I think Google Earth, or there is also some other programs available. So, and then you have here the Colorado Plateau, yeah, and it forms here like an island because here you have this strongly formed rocks, here you have the Rocky Mountains, here and here you have the what? The interior, yeah. So, and here that is then not deformed, and here it's highly deformed, and that is because of the subduction which dips here from the North Atlantic beneath here, yeah, beneath here. So, and now I was thinking about why is it here deformed, undeformed, and here deformed? Because if you are dating all these rocks, then they are all the same age. It is all Archean stuff, yeah, 2.7, something like this, yeah. So, and then the question is why they are here deformed and they are undeformed. I mean, if you are looking at this, then it must be, there must be something inside what stabilizes it here, yeah, or there is something going on in the underground, yeah. So, and that was something which has Alfred Wegener in 1912 not recognized, yeah, because Alfred Wegener, that was the father from the plate tectonic, yeah, you know plate tectonic by now, yeah, a little bit at least, yeah. So, and that he made just a two-dimension model, yeah. So, and therefore you have just studied old maps, yeah, from the old guys, you know, which they are sailing around, or later on they used then steamboats. So, and then he just connected the continents with each other by the shape, yeah. I mean, if you are looking especially for Africa and South America, that fits together like as on the pole, yeah. So that that fits together, yeah. So yeah, let us continue. So anyway, and there here is the sun, yeah. Yeah, that is this volcanic neck. So and I thought that there must be something in the underground, the third dimension, which Alfred Wegener forgot in 1912, and then I came 2,200 years later with my new theory. So yeah, next. So then the first thing what I used, that was I used a data set from Susan Vanderby. She is from Dutch, yeah, from Netherlands, and she put everywhere seismic station in the whole United States, and also in some other parts of the world. And then I was checking if there are some anomalies, yeah. So that is then very, very important to know, because then you can observe just by using the seismic stations, and we have still I have still planned to use a double hour in ES301 for where we are discussing the geophysics, yeah, but a little bit more in detail. So and there I didn't no, I can explain it now. So and here we have the Colorado Plateau, and here the white dot, that is the sun. And here we have then used the S waves, yeah. I mean the P waves are the fastest, then you have the S waves, and then you have the phase waves. So in these P waves, showing here an anomaly, yeah. I mean P waves are normally measured, S waves are normally measured in kilometers per second. So but here we have the anomaly, which shows that if these waves are a little bit faster or slower, yeah. So and if these waves faster or slower, then there is a reason behind, yeah. So and I mean here I have just checked the whole thing on in Moho, yeah, you know Mohorovic, the Yugoslavian guy, yeah, who made the Moho. And that is in a depth of about, an average under the continental crust, in a depth of about 33 kilometers. So and there is actually nothing, yeah, it is dark blue, and there the P wave, the S waves are even a little bit faster, yeah. So and that means the rocks from the continental crust there are very dry. So because if the rocks are very, very dry, then they are more strong, yeah. So then the strength from the crust there is higher, yeah. So maybe the surrounding material is the more soft, yeah. So, but if you are going then down in a depth of 70 kilometers, that is beneath the Moho, we have then a difference, yeah. We have then here S velocity anomaly of about, yeah, that is something like this, minus 350 meter, yeah? So that is minus 350 meter. That means the waves are, the speed of the waves is lower as it's supposed to be, yeah? Because you are using their standard measurements from the lab from here, yeah? So if it is lower, that means you have either a melt pocket beneath, like here. Here they are also slower. They have a very slow underground, yeah? Because there is melt beneath the underground. So, or it is wet. Yeah? You can have a flat subduction, and then you don't have a mantle wedge, and therefore it is then wet. Yeah? Because you cannot create melt. Or less melt, yeah, you have the higher, that means the underground is more weak, and here the crust is more stable, yeah, and therefore it forms this plateau, yeah. You have this plateau also in Tanzania. You have it actually everywhere where the old buttons are sitting. They are more straight, yeah. But the fact is that the whole thing is here of the same age, yeah. I mean, if you have an old plateau like the Tanzania plateau that is 2,900 MA old, and the surrounding material is then 2,500, and the next guys are 1,800, and the next guys are 1,000, and then you have then a few 640. So, but here it's all of the same age, so there must be a physical reason why it is here deformed and they are undeformed. Then we are going here with a depth of 90 kilometer. Then we have here already a seismic velocity of minus 400. With 110 kilometers, then we have here a seismic velocity also of about 400. Yeah, you can just compare the color. So there is then something in the underground. Yeah, otherwise you would not have this. Yeah. So then you are going. Here we are sitting then in the depth of 130 kilometers. We have here also, yeah, like minus 350. So if we are going down to 150 kilometer, then it becomes then faster. Yeah, I mean here we have then just minus 100. So in a depth window of 130 kilometers, 130, 110, 90. 70, yeah, we have here something which creates this anomaly in the underground with a thickness of about 60 to 70 kilometers, yeah. So then we can continue. So that the surprising thing is a thickness of 60 to 70 kilometers. That could be a slab, yeah. I mean, this is a very young subduction here in Colorado, yeah. That is. I don't know, that is 60 million years, yeah, that is actually, I mean 60 million years ago, Fiji was even not there, yeah, but that is actually, for in Earth's time, it is very, very young, yeah, that is not that old. So, and then such a slab could have a thickness of 60 to 70 kilometers. Normally they have 80, yeah, but maybe, you cannot solve it, the problem, you cannot solve it with such a high resolution just by using geophysics, yeah? So, and now what we can see, there is something going on, yeah? So, and this anomaly that is caused either by the influx of melt or by hydration in the underground. That makes the stuff also very, very weak. And that is now also for you as a applied geologist important to know, because all these anomalies, what you can see or observe everywhere, they are running the earthquakes, yeah, because you have always hot material, cold material, strong material, ductile material, and all these differences, yeah. So, and I mean here they have quite heavy earthquakes, not at the Colorado Plateau there is quiet, yeah, but in San Francisco, you know this, yeah. In San Francisco sometimes, but of course, I mean there is subduction, yeah, there's directly the subduction, and you have the Andreas fault system. And I mean, if you are going to San Francisco, it is also very, very hilly because of this subduction. And they had in 1910, I thought it was in 1910, a very strong earthquake. The whole town was destroyed, and the problem was all the gas lines, you know, they were running on gas, they stirred, and then everything was also inflamed, yeah. So yeah, that is the next slide. Now you can go to, because I have then studied these mantle rocks, yeah, to check if they are wet or if it was melt or whatever it was. Now we are going down to my paper. With this stuff we are continuing next week. No, this one. So, and then I found out that we have some fertile rocks, yeah. So, and there you are doing again a work on thin section, yeah, and then you can see that is actually very important, and therefore you actually should do work on thin section, but we are not offering this course. Anyway, you have here a garnet crystal. You know what a garnet is, yeah? That is this, and they are looking under the electron microprobe like this, and then you have this heavy fitting quints, yeah? So, and these are alteration. That is alteration. So, and that shows you they came in contact under relatively high temperatures and pressures, and then you are forming this heavy fight. So, and that is caused by the influx of water. So, and then you can, or I have done, you know, also such distribution maps. Here we have the silica distribution, yeah. So, and then we are going up a little bit. And here we have the magnesium distribution. Here we have the aluminium distribution. So, and now we have here some other figures. So, and there I could observe that we have here in the grain boundaries antigorite. So, and you know antigorite, that is that was formerly an olivine, or it was an autopyroxene, and they become then, when they are coming in contact with water, then they are forming an antigorite, that is a serpentine, and here we have an antigorite and not a lizardite or a chrysotile, because these guys have been maybe formed at much lower temperatures, but the antigorite, that is a mineral, or this serpentine variety, which forms at about 600 degrees Celsius, yeah? And I mean on the 600 degrees Celsius we do not have on the Earth's surface, yeah? So, and here the next thing was, here you have just everywhere, this olivine grain here is cross-cutted now by antigorite veins, yeah? And therefore you can just write down a mineral chemical reaction, and then you can calculate under which pressure and temperature conditions this happens here. Next slide. So here you have also calcite inside, yeah, in these veins. That shows us the fluid was not only a pure water fluid, you have also some CO2 inside. Otherwise you would not form calcite. Here you have then again a former garnet grain which is now catified. So, and here the same, and here the same. So, we are just going through. So, and then you can make these PT diagrams and reconstructing the uplift story. Here we have the peak metamorphic conditions from our rock, yeah. That is a little bit by 5 GPa, that is in a depth of 160 Ks, yeah. There was the rock originally formed. That fits with the 150 Ks. So then it was uplifted to stage 2. That was then about in a depth of about 110 kilometers, yeah, that fits also with geophysical observations. Then it was cooled down till 0.3, that is then 600 degrees Celsius. That is there where we are forming then the antigorite, which I showed you just before. And then it was uplifted to the Earth's surface, and then I came and have sampled it. So and now we have such different things. I studied then the fluid flow, yeah, because I mean this fluid must go through. So and that is the thing why I'm telling this in connection with the thing in class today. How can you find out if the fluid flow, if it was mobile, so that the fluid can go through, yeah? I mean, in Colorado, you have also the Colorado mineral, right? You know this, yeah? So in there you have a lot of minerals which are enriched there, caused by fluid flow, and these are, you can find hepatites and such things, yeah? So, but the fluid must come from somewhere, yeah? So, and then this is then a picture from thin section, this as well. So, and then you have here open cracks. In open cracks, you cannot measure anymore any fluid inside, yeah, because it goes out, yeah, it disappears. And if you are measuring something in these open cracks, then it is just wrong, because that can be just come in with at the surface, yeah. So, but then I have also studied totally embedded cracks. I'm doing now all this, the same studies on the Fijian rocks, yeah, from Peru. Yeah, I have done a lot of measurements. I'm doing these measurements now in Melbourne at the synchrotron. These measurements, which I will show you then, we have done in Germany in the synchrotron. So, but if you are studying totally embedded cracks, yeah, they should give you the last snapshot before the whole thing goes up, yeah. So, or you can check mineral inclusion inside the mineral. This you can all do with just using a microscope. So, and then I have checked, yeah, if you just can go up, then I have checked the grain boundaries, yeah. So the grain boundaries here between the mineral grains, they look like this, yeah. So, and I showed you just before in this sketch map, yeah, you know from the class, yeah, this temple, how this look like, yeah. So, and if you have such grain boundaries here, then you can create a network, yeah. So, and then fluid flow is possible, yeah. It just goes through the rock, yeah. So, but that happens at high temperatures, at least 600 degrees. I have just measured here the antigorite, if it is really an antigorite, and these peaks are here, typical antigorite. So that happens at 600 degrees Celsius, and here we have a totally embedded crack, and this embedded crack was serpentinized. So it was at first open, so and then it closed, it was then just a lead. So and then I could identify such a totally embedded crack that is 50 micron, yeah, that is not too big, yeah. So and then I have analyzed them. So through such grain boundaries, an interconnected fluid flow is possible, and then we are going there. So in this interconnected fluid flow causes then this seismic anomaly, yeah? I must not explain the table is boring, this one as well. So, and therefore I'm using them always synchrotron based FTIR. FTIR, that is a Fourier transform an infrared spectrum, and with the infrared line you can detect the OH groups in your minerals, yeah? So again in the laser light we have here the alpha peak, you know that is an alpha direction, you know every crystal has 3 directions, yeah? And now we are looking here where the monomineralic crystal is. It does now not matter if it is monomineralic or not. This one is a monocline, sorry, not monomineralic, monocline. So, and then you have the three direction, alpha, beta, gamma, yeah, you know this. That is something like a polygon, yeah. So, and then I'm measuring always in all three directions, and this peak here, these are the OH peaks, yeah, to detect if there is some OH in the mineral, yeah. Because I mean, if you are looking at the mineral chemical formula from an olivine, there is no OH, yeah. So, but the OH can be on the point defects, yeah, you know, if there is a gap, or if there is a crack, yeah. If there is a crack, then you have a gamma defect structure, and it can be hosted a lot of OH. Not really a lot of OH, I mean, you will see it then, it's just a few ppm. So then the next thing what I have done here, so yeah, then you can measure just the polar figures, yeah. By using the polar figures, then you can check if this olivine was deformed or not, yeah. And these guys were a little bit deformed, yeah. I mean, here it is in 1, 0, 0 direction. 1, 0, 0, that is then this one. If you have such an olivine that looks like this, and so something like this is. So, and then the 1, 0, 0 direction, that is this one, that is the 1, 0, 0. You know this from ES301, I can't remember if I have done it. It does not matter. Then we have here 0, 1, 0, and that is then 0, 0, 1. So, and then you are measuring just in all three directions. So, and then you can see they have slightly been deformed, yeah. If they are strongly deformed, then they are just going scattering around, yeah. So then you can check this, how far they are deformed. That is a very important thing, because if we have an earthquake, yeah, I mean in ES301, Eleanor told you by an earthquake, I mean you have stress and strains in the mantle, yeah, more ductile material, more brittle material, and then you are creating an earthquake. So, but the trigger that is mainly hosted in the mantle, and the main rock forming mineral in the mantle, that is the olivine. And if the olivine, if there is too much water, then they are just flipping the axis. So, and then you are creating a collapse, and then you have your earthquakes. That's the way how it works in detail, yeah? Because the axes are then flipping. So, then next slide. So that was then now my model, yeah. So here I made this measurements. I'm making there such maps, 40 by 40 micron. So and every map contains of about 540 spots, yeah. Because with the synchrotron I got a resolution of about 3 micron every point, yeah. And then I have here a lot of points, yeah. So again, and here we have the totally embedded crack, yeah. So and then you can see around here we have the shape of a crystal, and here we have the totally embedded crack that was maybe formerly a monomineralic rock, as I showed you before in the PowerPoint of the class. And then this crack is annealing, and then you have still the snapshot from this totally embedded crack, how the fluid flow was while this rock sample was still sitting downstairs. So, and here I have analyzed it against the totally serpentine in an annealed crack. Yeah, I showed you the image before, and there the water content rises then up up to 1400 ppm, yeah. So and here we have then maybe up to 600 ppm. So if you have just locally, if you are just sitting on point effects, yeah, then you have not that much. You have here maybe 150, yeah. But this stuff weakens the mantle, yeah. So, and I have done this also now for the Poro sample to show the people if there is a possible earthquake or not. I don't think so, because these samples from Poro, they were formed in a depth of 90 kilometers and the 90 kilometer depth. They have also with geophysics and seismic methods nothing detected, yeah. And the stuff from a depth of 400 and 600 kilometers I cannot reach. So because this volcanic eruptions, the melt for them was not created in such a depth. So the next slide. So that is the 3D map from this totally embedded crack. Here you have the olivine antiboride transition zone, and here you have the antiboride. So and now we are going again down to the model. So and then I have proposed following model, you know, that could be or not, yeah, because then we have here this flat subduction, which leads to the hydration of the subcontinental mantle here, yeah, and the hydration of the mantle mesh. So and this hydration is caused by the release of water from this hydrous minerals inside your slag, yeah. So again you have then here hydration, and that makes the zone here very weak. So here we are sitting directly beneath the plateau. So and you have then the breakup of the slag, because you have to bring, at first you are hydrating the whole thing, yeah, which causes that you have here a totally wet zone, and that you can analyze, yeah, with geophysical methods as well. So, but then you have to bring in all the samples from my PT calculation from here. Yeah, 150 kilometers, they are coming then from here somewhere, yeah. So, and then you have to bring them up, yeah. Here is the volcano or the volcanic neck. So, and then you have to bring them up, and therefore you need an eruption, yeah. I mean, if you are looking at this rock sample from Poro, yeah, you have it right now in your hands, yeah. Then I mean, here is the xenolite, and there's material around this basalt, yeah. So in the basalt, I mean, that is from a volcanic eruption, and then it brings this sample up, yeah. It is just a carrier, like the kimberlite or the diamonds, yeah. So, and therefore you need the influx. Therefore, you need the influx of hot melt, and I have interpreted this as a break-up of the slag, yeah. And then I can also see by using the geophysics, and then I could sample this sample there, and then is the story behind, yeah. But as I showed you in these backscatter electron images, as well as in under the microscope, there must be, for that you are making it ductile there and getting these geophysical anomalies, there must be interconnected fluid flow, yeah. Otherwise you cannot make it ductile, yeah. So, and these are the things which I will continue that next week in our layered intrusion class, how it looks like then theoretically, and when you can have an interconnected fluid flow or interconnected network of fluid flow, and when not, and therefore I have done some sketch maps done.